Hi, my name is Eric Lauer, and this is my final video for my ET255 final project. So we know that NC State University is the largest university in the state, and that being said, we consume enormous amounts of energy of all types. We know that sustainability is often equal to savings, so we are constantly looking for ways to offset our energy usage in responsible, cost-effective ways. We have many lands and labs available for our disposal to produce energy due to our large agricultural and natural resource school. So for this project, I was asked to compare several resources and their effectiveness to offset some of our large energy bills. I've decided to discuss growing corn on a portion of hill forest land, along with using poultry and dairy cattle waste from our field labs to produce cost-effective offset to our annual energy demands in a couple different sectors. So I'll break those down for us now. First off, the potential to grow corn on hill field land for ethanol fermentation is pretty promising. Hill forest seems like the right candidate for this. Due to its large size, it would be a little bit more worth the effort to convert to agricultural use since we're dealing with thousands of acres compared to hundreds on our other forests. Like I said, fairly intensive land conversion processes would have to occur, but in comparison to the methods for short rotation woody crops that just aren't quite there in efficiency yet, I think corn is the safer bet. Out of the 2,500 acres that the hill forest encompasses, I think that easily half to 1,500 could be used for growing corn and producing ethanol, which leaves about half for summer camp or other university activity usage. Corn makes glucose, which we can break down and convert to ethanol using fermentation, and while leftover products and crops can be used for incineration. Due to our large demand for fuel, I think that fermenting corn for ethanol would be a safer bet than using incineration to burn it for energy. I lost my place here. Here we go. So like I said, I do believe that fermenting corn for ethanol would be much more efficient than incinerating it. The fermentation process for corn is already tried, true, and effective. We do it every day on a commercial scale here in the U.S., so we have pretty solid numbers on the conversion process. So for 1,500 acres of land in the hill forest, we would get 79 to 8,000 pounds of corn an acre, which in turn can make 495 gallons of ethanol, yielding a whopping 37.5 million BTUs per acre of corn. So at 4,995 gallons and 37.5 million BTUs per acre, it gives us a grand total of roughly 742,000 gallons of ethanol and 56.5 billion BTUs from fermentation of corn every year. So that translates to nearly half of our fuel consumption here at State, with a potential for nearly 2 million in savings. So the pros and cons of corn. Startup costs are always going to be a bit pricey, such as planting, maintenance, fertilizer, and everything for the first year. But after that, costs are pretty straightforward for growing corn. The costs are going to stay pretty steady and reasonable, especially if we can use existing university equipment to harvest this corn. And then if ethanol fermentation facilities were built on site, they could be used educationally with the summer camps, as well as making the final ethanol product a little bit easier to transport as a liquid fuel the short distance to the university. So corn and incineration, we can use corn in a different process, incineration, to produce electricity for the university to use. But various barriers prevent it from being as promising as ethanol production. To begin with, the hill forest is a little bit farther away, and transporting the raw feedstock or the electricity that feedstock produces over that distance would be a little bit tricky. Incineration is also just burning plant products, and so why really invest in that process if we have cleaner ways to produce electricity that are constantly becoming more feasible? Excuse me. And if corn were used for incineration, it could produce slightly more BTUs per acre at 60 to 63 million, but in a less efficient form, in the form of pure heat or energy, and that could be difficult for us to transport and manage in order to utilize it best for direct savings. So that brings us to our agricultural resources we have here with huge potential to produce biogas for the university. I'll be talking about poultry and dairy cattle waste and how we can use it in either anaerobic digestion or gasification to yield biogas. So here at State we're working with about 190 dairy cattle and 4,500 chickens. So typically an anaerobic digester calls for slightly larger farm operations than we have going on here, but we do have the unique position of being a research university with an educational budget, and the investment in an anaerobic digester would be a great learning tool for students, along with giving the biogas and agricultural research programs room to grow on this new technology. So breaking down the numbers for anaerobic digestion, poultry produce about 72 cubic feet a day per 250 chickens of biogas, so that yields about 1,300 cubic feet a day total. And while dairy cattle, one cow can produce about 44 cubic feet a day, giving us about 8,300 cubic feet a day total from the cattle. That's 43,000 and 26,000 BTUs a day per animal, respectively. And at biogas burning at 600 BTUs per cubic feet, that yields 774,000 BTUs a day for poultry and nearly 5 million BTUs a day from our 190 dairy cattle. So offsetting our energy usage, we do use more natural gas than any other fuel. So biogas produced from either poultry or dairy wastes could offset anywhere between 300 million to almost 2 billion BTUs from our current trillion BTU natural gas budget every year, saving us potentially thousands, if not millions of dollars. So pros and cons of anaerobic digestion. Like almost any project, startup costs are going to be pretty big. But once it's established and we start producing biogas and offsetting our energy usage, we will get payback on that. So the number of livestock we keep for research can only grow with the school, providing us more waste and providing more research opportunities for the years to come, and continued usage for the investment in our digester, while at the same time we can shrink our natural gas budget. So now let's talk about these two feedstocks, same two, poultry and dairy cattle, with respect to gasification instead of anaerobic digestion. The gasification process is slightly different. It can be scaled a little bit easier and it's a bit more established, although the syngas products that it produces burn cooler per cubic foot than the biogas produced from anaerobic digestion. So while again startup costs for gasification are going to be high, just like with anaerobic digestion, there are tons of student opportunities in a potential program such as this. So the numbers for gasification, similar to anaerobic digestion, break down like so. Poultry and dairy still produce 72 and 44 cubic feet a day, respectively. But burning at a slightly cooler BTU per cubic foot, which is 1 to 200 for the syngas compared to about 600 for the anaerobic digestion biogas, that gives us 7,200 to 14,400 BTUs a day for poultry, and 44 to 8,800 BTUs a day for cattle. So that is a little bit lower of an energy potential for the gasification process. Which leads me to the point that I think anaerobic digestion would beat out gasification as the best and most sustainable practice that we could use to offset our natural gas usage. After we bridge startup costs for the facilities and technology, startup costs are going to be fairly similar, but anaerobic digestion could produce more BTUs with the same amount of livestock. And that's pretty much all you need to know right there for the sustainability of it. That also leads me to the point that I think using our dairy cattle waste in anaerobic digestion would be better and more sustainable than using corn as an energy crop to produce ethanol for the university. Using this biogas we produce from our cattle could lower our wastes at our labs while at the same time reducing the smell and providing research opportunities for students while offsetting our largest fuel cost on our budget, which is natural gas. And we could offset it by millions, if not billions, of BTUs per year. Also, our field labs are fairly close on Lake Wheeler Road, and so transporting that biogas to the university would be fairly cheap and easy. So out of the three feedstocks I've discussed, the one I think would be the best to pursue if we were looking for a sustainable practice would be the biogas and the anaerobic digester. It beats out corn for lots of reasons. Short rotation woody crops, like I mentioned earlier, they're still being in the process of being perfected for biofuel use. And while converting a large tract of our hill land to agricultural use for corn and other energy crops would be doable and feasible, our field labs already exist with our cattle there, and we wouldn't have to disturb any land to start that up, which cuts down our initial costs significantly. Second, while ethanol would be slightly easier to transport than biogas, we would have to dilute it to use it in conventional gasoline engines, and that increases our facilities and our costs, and it decreases our direct savings into the budget when compared to just replacing natural gas with biogas. Thirdly, growing corn every year, it wears out the soil, and many would like it to stay undisturbed. It is a forest now, so like I said, it would be a lot of big change and a lot of work, and arguably worse for the land. While our cows, they're already there, they're not going anywhere, and if anything, they're going to grow in number. Fourthly, our field labs have plenty of space to build biogas facilities in close proximity to the actual livestock, which would significantly decrease our transportation costs. And so wrapping that all up, natural gas is one of our biggest expenses at $8 million a year, and the generation of biogas from anaerobic digestion processes would produce the most and the hottest burning gas to offset our current natural gas bill in terms of dollars and BTUs. And that is the end of my presentation. Thank you very much.